YouTube channel.
Good afternoon. So today is a deadline for homework number 2. I extended the deadline for homework number 2. So please submit it by tonight. So please submit your homework by tonight, homework number 2. And today we go to lecture slide 5. Okay. Any question from previous class? Nobody? Any question? You guys can hear me?
Yes, Professor.
Okay.
Yeah.
If you do not reply, I have no idea.
Yeah, I don't have no question personally.
So if you do not have any question, let's go to the today's material, which is chapter 7 of your textbook. Which is the quicksort. Anybody ever did quicksort before? Ever used quicksort?
I haven't.
Yes, Professor.
Yeah. So what was your experience with the quicksort? Is it really quick, as the name says?
It is like comparatively, it is really quick.
Yeah, it's really quick, actually. The name replies. And guess what? Why is so quick? What's the reason behind? So, anytime you use some language, any programming language has some built-in functions. One of the function is a sorting function, actually, like C++ and Java. Without surprise, many languages, when you just call language-specific sort function, underneath, they implement this quicksort because it is one of the most efficient sorting algorithm known. It's a beautiful algorithm, actually, along with the merge sort. So let's look at the quicksort today. It's quite old, actually, 1962, by a guy named Hoare. And it is an algorithm of the divide and conquer paradigm. So anybody can tell me what's a divide and conquer paradigm?
Dividing the array into half until we get to the last element and then rejoining it back.
So divide and conquer. So you have one big complex problem. To solve that problem, you first divide into smaller, more manageable pieces, and then solve those smaller manageable pieces one by one. It's easier to solve smaller problem than one big original problem, right? So solve smaller solve problems and later combine the solutions, all those smaller solve problems. That is your actual solution. That is a divide and conquer. It is a paradigm not only for computer algorithm, but even in the traditional war, right? When you attack somebody, right? You try to divide your enemies into smaller pieces and conquer them one by one. So it's not something unusual. And I believe, many of you ever programmed in divide and conquer approach already. So I just let one person in. So please don't be late to the class because the class is halted because of you who came in late. And another characteristic of quicksort is sort in place. Anybody can tell me what is in place sort is?
Like instead of dividing and making another sub-array, it will be sorting inside the same array.
In place is in opposite to out of place, meaning you need some extra storage space to solve some problem. So think about insertion sort, refresh your memory. How does it work? You keep rearranging your element one by one, right? Within your input array. If you have input array, starting from the first one, you just permutate, you rearrange it one by one, element by element. So you do not need any extra memory space. There is an in place sort. If you remember the merge sort, you do need some extra storage space. When you need extra storage space when it comes to merge sort. Anybody? Why merge sort is not in place sort? Because of which routine? Merge. When you merge two subarrays, right? You need some extra storage space. Remember, you take in half the merge sort. Keep taking half until you cannot take in half any further. You have a single element, and then you start merging together. Whenever you merge, you need extra storage space. So quicksort is quite popular and attractive because it does not need any extra storage space. Okay. When you need any extra storage space, not only it is wasteful when it comes to managing your storage space, but you need to reserve some storage in your memory, somewhere in your heap. And then once you're done, you have to deallocate the memory space. So not only the memory is involved, but also the time to allocate and deallocate the memory space is involved. So in place versus out of place, both in terms of memory usage and time it takes, there's a huge difference, especially when input size gets bigger and bigger. So anybody can remember the running time of insertion sort asymptotically is order upper bounded by n square algorithm, right? In the worst case, it's quadratic to the input size. That's the running time of insertion sort. How about the merge sort?
N log n.
N log n. In the worst case, it is n log n. And I told you from time to time in my class, the difference between n squared and n log n, it becomes night and day difference when input size n gets bigger and bigger. Okay, so how about the quicksort algorithm? What's the running time of quicksort? The naive quicksort is order n squared, which is same as insertion sort, but with slight of tuning. Slight of tuning, it becomes n log n, just like merge sort. So it takes good from the both sides. In terms of running time, the running time is same as the merge sort, asymptotically. In terms of memory usage, it is same as insertion sort. So it can be better than that. And in real life, it's even better than the merge sort in terms of the running time, because it doesn't need any extra storage space, meaning it doesn't need to allocate and deallocate memory space. So same running time, n log n, but constant factor multiplied to n log n is different to the merge sort and quicksort. Quicksort is much quicker in real life. So we're going to look at that in today's class. Okay, so let's look at the quicksort. It is a divide and conquer algorithm. And let's assume we want to sort n element array. This is your input. Step number one on the divide and conquer paradigm is divide, obviously. Okay. Partition the input array into two subarrays around a pivot, let's say X, into two subarrays around the pivot, such that elements in lower half, the first subarray, is less than or equal to pivot element X, and pivot element X is less than or equal to any element in the upper subarray. That is a divide. Okay, so initially it's all mixed up, the order, relative order of the elements in input array. After the partition, you can separate your input into two parts, first half and second half, around the pivot. First half, lower half of the pivot is all less than or equal to X. Of course, lower half, it is not sorted yet, but at least anything in the lower half is less than or equal to pivot. So let's say pivot is 5. So lower half might be 3, 1, 2, 4. 3, 1, 2, 4, they are not sorted yet, but they are all less than or equal to pivot X, 5. Okay. Upper half, second half of the subarray, all bigger than or equal to the pivot. So it might be 10, 8, 9, let's say 6. Among themselves, they are not sorted yet, but all the elements on the right subarray is bigger than or equal to pivot. 10 is bigger than 5, 8 is bigger than or equal to 5, 9 is bigger than or equal to 5, 6 is bigger than or equal to 5. So initially, there was no order between them. After first division, we have a little bit of order, actually, at least, because we separate your original input into two parts, first half and second half, around the pivot, such that first half is all less than or equal to pivot, and second half is all bigger than or equal to pivot. That's the divide part. This is most crucial part of the quicksort, which we call partition. Divide in quicksort sometimes we call partition. Partition the original array around the pivot. Okay, this is most important routine in the quicksort. So to understand quicksort, step number one, you have to understand the partition. Once you divide, then second, recursively call the quicksort in first half and the second half, two subarrays. Two recursive function calls, trivial. And then combine. Once you finish conquer, then everything is sorted. So there's nothing you need to do. So divide and conquer paradigm. Step number one, divide. Step number two, conquer. Step number three, combine. In the quicksort, all the hard and dirty work is done in the first part, which is divide. Do you remember the merge sort? Another divide and conquer approach. Okay, divide. What did you do under the merge sort? What did you do in the divide?
Split the array in half.
You keep having the array in half. Yes, exactly. That's a divide, right?
Right.
So again, because someone who came in late, I have to start all the way from the beginning again. So divide part is trivial under the merge sort because you just keep having the original into same size two subarrays. Okay. What is conquer under the merge sort? Recursively call these two same size subarrays. Same thing as quicksort. Two recursive calls. And then combine. What did you do at the combine? Step number three under the merge sort.
Like merge the two.
Merge, right?
Yeah.
So divide, you keep having your input into two subarrays until you cannot do any further. And then you start merging together. That's combine. So same divide and conquer approach, but merge sort, all the hard and dirty work is done from which part? 1 to 3.
1.
Combine, 3. Merge. Compared to quicksort, all the hard and dirty work is done under divide part. So you can say merge sort is nothing but recursive merge. Step 3, combine. Recursive merge. And quicksort is nothing but recursive partition. Because divide is the crucial part of the quicksort. Get the big picture, okay? Do you remember the running time or time complexity of combine of the merge sort? Merge? Order n, right? Order n time merge routine. And 2 recursive calls of size n over 2. So it reads n log n time. Guess what happened to the quicksort? all the hard and dirty work is done divide. So divide should be efficient. If divide is not efficient, the running time of quicksort won't be good. You're going to see pretty soon, divide takes linear time. That is where the efficiency of quicksort comes from. You can rearrange the element of your input around the pivot area, first half and second half, in the linear time. And then conquer two recursive cores of size n. You add these guys too. So it is what? 2 times t of n over 2 plus order n, which is order n log n, actually. That's what you're going to see from today's class. So let's look at the partition subroutine, which is the most crucial part of quicksort. Divide. Again, this is nothing but the partition. Okay, so let's see how partition works. Partition, input array is A. P is what starting index, and Q is the ending index. A of P through A of Q. That is your input to the partition. Okay, so if you look down there, this is your input array. A of P through Q. You start from A of P and end at A of Q. Okay, so the first thing you need to do inside the partition is choosing a pivot. In this algorithm, I just choose the leftmost element of your array as pivot, which is A of P in this case, starting index. Your textbook actually choose rightmost index A of Q as your pivot, but the same thing virtually. So the simplest partition algorithm, choose, let's say, leftmost element each time as your pivot. So A of P, leftmost element, becomes pivot X. Okay, and then we adjust to index I and J. Index I starting from pivot P, and index J starting from P plus 1. So I plus 1. Okay, so initially I is looking at index P and J is looking at index P plus 1. That's a starting index of indexing value of I and J. And we loop through index J from P plus 1 through Q. So J will range from I plus 1 or P plus 1 through all the way through Q. Okay, so what do you do inside the for loop? Keep checking every element. And if, let's say, some kind of violation to the invariant happens, you do these things. So what is an invariant? At any given moment during the partition, let's say I advances to somewhere here, and J advances somewhere here. Any element from A of P plus 1 through A of I should be less than or equal to pivot. And I plus 1 through J minus 1 should be greater than or equal to X, the pivot value. From A of J through A of Q, we do not know yet. This is an invariant. Again, remember, up until index I, less than or equal to x up until index j minus 1, starting from I plus 1, greater than x. Okay, so let's start. Starting value of index I is p, and starting value of index j is I plus 1. Then this invariant hold at the beginning. What did I say? Up to I less than or equal to x. Initially, I is looking at just p, just one item. So a sub p, of course, is less than or equal to itself. How about j? J start from I plus 1. I plus 1. But invariant says up until j minus 1, it should be greater than or equal to x. J minus 1 is nothing but I when you start, initial value. So x is greater than or equal to x. So invariant hold at the beginning. Okay? And you keep incrementing I and j during the for loop iteration. How? Keep checking a sub j. And keep checking a sub j and check whether a sub j is greater than or equal to x. If a sub j is greater than or equal to x, then you are fine because you simply increment j by 1. It effectively extending the size of a sub I plus 1 to j by 1. But if a sub j is less than x, then you are in trouble. Do you follow me? If a sub j is less than x, then we are in trouble. Why? Because when you increment index j by 1, new j, anything up to j minus 1 should be or bigger than or equal to x, but this guy, a sub j, now suddenly become less than x. Violation to this invariant. Then what should I do? This guy, violence, should be exchanged to non-violent invariant, which is what? I plus 1. Up to I less than or equal. So I plus 1 is bigger than or equal. So these two guys will be swapped. Look, inside the if statement, you increment I by 1 first and exchange a sub I by a sub j. So increment I by 1 and change a sub I plus 1 with this a sub j, which violate our invariant. Then what happens? Less than or equal to guy, go to a sub I plus 1. And greater than or equal to guy, go to a sub j. So when you increment j by 1, everything's fine. Now you have one more element, less than or equal to x, on the left half. One more element, greater than or equal to x, on the right half. You keep doing this until j fall out to a sub q. You need one more thing to do, which is what? Exchange a sub p and a sub I. Put your pivot into your proper location. That's it. That is a partition. Okay, so let's look at the example, how this works. By the way, what's the running time of this partition? I said it's a linear time. Is it really linear? Constant time operation. Constant time operation. Now we have for loop. This for loop starting from p plus 1, which is I plus 1 through q. So it's looping n times. Inside If we have a violation, you simply swap, exchange a sub I and a sub j. So this is constant operation. So for loop runs order n, set of n time. Finally, exchange a sub p and a sub I, another constant operation. So overall, you sum this up, it is what? Linear time operation, order n. Now, let's see how it works. We have original input array like this. Now, what's our pivot? Leftmost element, x, pivot.
Professor,
Yes,
we always pick the leftmost or the rightmost. We cannot pick from the middle.
well, I'm gonna go there later on, okay? So for the time being, let's do the simplest way. You stick to either keep leftmost element or rightmost element,
Okay.
okay?
Thank you.
I'm gonna go there. So pivot is leftmost element. Index I starting the pivot, index j is I plus 1. This is the initial value. Now refresh your memory. Our invariant. Everything up to I is less than or equal to x. Everything up to j minus 1 is greater than or equal to x. So I'm going to write down, draw a picture, some pivot, and I and j. Everything up to I is less than or equal to x. I plus 1 through j minus 1 is bigger than x. Okay. So does invariant hold from the beginning? Up to I is 6 less than or equal to 6.
Yes.
Yes. How about j? Up to j minus 1. Up to j minus 1. J is 10. So j minus 1 is 6. Is it greater than or equal to x? Yes. 6 is greater than or equal to 6. So invariant hold at first, at the beginning. Now we are going to the for loop. We keep checking and we execute this body of the if statement only when a sub j is less than or equal to x. If a sub j is bigger than x, we simply increment j by 1. So let's start. Check. A sub j, 10. Compare with the pivot. If it's greater than your pivot, you're fine. Simply increment j by 1. 10 and 6. Bigger? Yes, 10 is bigger than 6, so we are fine. So j goes by 1. Now compare 13 with your pivot. A sub j and a sub x. Is it bigger?
Yes.
If it's bigger, you're fine again. Look, when it's a invariant, violation of invariant, when a sub j is less than or equal to x. If it's bigger, you're fine. If it's less, you need to do swap. What do? You increment index I first and then swap a sub I and a sub j. So again, compare 13 and 6. A sub j is bigger than a sub x. So fine. So keep moving. Until what? Until you find the violation. Now, you see a violation?
Yes.
Yes, a sub j is indeed less than pivot. We have a violation. Okay, then what would you do? Increment I first. So now I becomes not this and this. And then swap these two guys. Then you have 6, 5, 13, and 10 because you swap 10 and 5. Remember, you do not swap I and j, but I plus and j. Okay. Now, I is incremented by 1. And j is looking at 10. And still, this guy is a pivot. And keep searching until violation of invariant. 8 is bigger than 6, so we are fine. How about 3?
Is less.
3 is less, right? So indeed, violation. So what would you do? You
You
swap these 3 with what? I plus 1, not I.
With
I
13.
plus 1 is 13. So 13 and 3 will be swapped. So 3 and 13 will be swapped. Now here I and j. And j move to the next element. Now, at this point, look at this. Does invariant hold?
No.
No. Up until here. We have a pivot. Up to I, everything should be less than or equal to pivot. 5 and 3, less than. I plus 1 through j minus 1. 10, 8, and 13 should be all greater than or equal to pivot 6. Okay? So this is our invariant from our picture right there.
Yes.
Up to I less than or equal to x. I plus 1 through j minus 1 greater than or equal to x. Okay? So, again, until you hear violation, you now swap I plus 1 and j. Keep going until you hit a violation again. 3. 3 is less than 6. So you swap with I plus 1 and j. I plus 1 is 13 and j 3. 13 and 3 will be swapped. Okay? Keep moving. Now another violation. 2 is less than the pivot, not bigger than the pivot. So 2 will be swapped with which element?
With 10.
I plus 1, which is what? 10. 10 and 2 will be swapped. Okay? So 5, 3, 2, 8, 13, and 10. Okay? So you keep increasing less than or equal and greater than or equal the first half and second half. You keep increasing this until you cannot do any further when j falls out of this array. Now j is 11. Fine, 11 is bigger than 6. So keep moving j. Now j is out of index. This is when you stop. Okay? When you stop, the final step is what? You swap your pivot with index I. So 6 and 2 will be swapped. Then you have this. So after the partition, this is your starting array. After the partition, your array looks like this now. Around the pivot, the first half all less than or equal to pivot. And all the second half is greater than or equal to pivot. Understood?
Yes.
So this is a partition. Okay. Look, we start from the first element, and then we simply what? Incrementing index j or index I accordingly whenever you see a violation. And when j falls out of the index, then that's when we stop. So this is what? Linear time operation. Okay. And then what? Recursively call the first half and second half. So probably I don't have that. Yeah, I don't have that. So quick sort, A P to Q minus 1, that is the first half. Q plus 1 through R, that is the second half. So let's go back to this picture. What would you do? The first half is this guy. Second half is this guy. Recursively call this and that. So recursively call this guy. What would you do? 2, 5, 3. So 2 will be your pivot. This is X. And I is a starting index or pivot. And J will be what? I plus 1. And we start again. The same partition. So 5 and pivot. Bigger than 2. So fine. So we move. 3 is bigger than 2. So fine. And then we get out of this index of the left subarray. Okay? And then what? Pivot and I, A sub I got swapped. This 2 is swapped by itself. There's nothing actually. And then we successfully what? Partition the original input into 2 parts, less than or greater than. Since there is no less than 2, there's nothing on the left side. On the right side, 5 and 3, greater than 2 pivot element. Understood? Now you recursively call left side and right side, which has no element, and then 2 elements. When you call quicksort or no element, you don't need to do anything. So you just return. Now, when you call quicksort on the right half subarray, 5 and 3, step number 1, do a partition. Again, leftmost element as your pivot. This is your X. And index I starting from the pivot, index J starting from I plus 1. Do you see a violation? Yes, A sub J, 3 is less than 5. So I plus 1. I plus 1 is 3. And then 3 itself will be swapped, which is actually do nothing. And then J goes out of index. I'm done. Okay. So once you do a partition, you recursively call the quicksort, the first step and second step. Keep going on. That is the quicksort. So to understand quicksort again, you need to understand this partition algorithm. This is a key. Now, let's go back to overall pseudocode for the quicksort. Quicksort of array A from index P to index R. So this is starting index P and ending index is R. If P is less than R, then call partition. Partition returns what? Partition returns the index of a new pivot, which is Q. Again, look at the partition code, return I. What is I? After you exchange your pivot with your ace I, so new pivot element index, that is index I. You partition original input around your pivot, and then you recursively call first half. So P through Q minus 1, because Q is what? Index of the pivot. And then quicksort Q plus 1 through R, the right subarray. There is a quicksort. Initial call quicksort, input array A from starting on index and ending index. Let's assume A sub 1 through A sub n. Now, let's analyze this quicksort. After you understand how the quicksort works, next step is try to analyze, get the running time of the quicksort. In this version of quicksort, we assume all input elements are distinct because the pseudocode, this naive pseudocode, does not really work well when there are some duplicates. But the original algorithm from the original guy Hoare works pretty well when input contains only even duplicates. So to make our life easier, let's assume all input elements are distinct, no duplicates. And let T of n is a worst case running time on the array of elements for doing a quicksort, the upper bound. So when worst case occurs then, when does worst case occurs? Look,
And it's in descending order.
after partition, right? After partition, you have some left side and you have some right side around the pivot. The best case is each time partition is called, somehow this partition is chosen like a median value of your input array. So there are equal number of left side and equal number of right side. That is the best case. You can evenly distribute the same number left side and same number right side. That's a best case of partition. Then what's the worst case of partition? When one side has no element and the other side has no element. When this kind of thing can happen, let's say input is sorted already. 1, 2, 3, 4, 5, let's say. You want to do a quicksort. So quicksort, step number 1, divide, which is partition. Choose leftmost element as your pivot and try to move your element around this pivot such that left side has less than the pivot, right side has bigger than the pivot. Now, after the partition, what happens? There's no element less than 1. So left side of pivot 1 is nothing, but right side is what? n-1 element, 4 elements. Everything other than pivot, all bigger than the pivot. So you have all the elements other than pivot on the right side. Understood? If you recursively call this right side, if you choose leftmost element as a pivot again, what happens? Same thing. There's no element less than 2, and every other element is bigger than 2. Okay? How about input is reverse sorted? 5, 4, 3, 2, 1. If you assume leftmost element will be chosen as a pivot all the time through partition, then what happens? After the partition, everything will go to the left side and no element go to the right side. Same thing when you recursively call the left side using 4 as a pivot. Okay, so if input is sorted or reverse sorted, then we have trouble. Because one side we have no element, and another side we have n-1 element. If the running time for the quicksort for an element is T of n, it is same as what? After the partition, linear time partition, theta of n. After the partition, you have 2 parts. Problem is one part, you have 0 element, so T of 0. And another part, we have remaining n-n elements. Every element other than pivot, so you have n-1 element to be sorted on another side. So T of n equals T of 0 plus T of n-1 plus theta of n. Everybody understand where this formula comes from? Yes? Yes or no? This is worst case. I'm waiting
Yeah.
for your reply. You get it up to this point?
Yep. Sort of. Yeah.
Yeah. Now, what is T of 0? The time to run quicksort with 0 element, constant time. Time for run to quicksort n minus element, let's temporarily just say T of n minus 1. And then partition theta of n. Now, theta of 1, constant time, will be absorbed into theta of n because this is polynomial. We're going to concentrate on the leading term eventually. So theta of 1 will be ignored. So T of n equals T of n minus 1 plus theta of n. This is what? Nothing but arithmetic series. So theta of n squared. That's the worst case of quicksort. Now, one way to compute this is like this. T of n equals T of n minus 1 plus theta n. Then what is T of n minus 1? T of n minus 1 equals T of n minus 2 plus theta of n minus 1. Yes? What is T of n minus 2? T of n minus 3 plus theta of n minus 2. We are using original formula, right? If you keep doing this until you cannot do any further, T of 1 equals T of 0 plus 1. You just add all the left side and the right side. Then left side of equality is T1 through Tn. Right side will be T0 through Tn minus 1 plus theta of 1 through theta of n. Now Tn minus 1, Tn minus 1 will be cancelled out. Tn minus 2, Tn minus 2 will be cancelled out. So eventually, on the left side of the equality, you have only T of n left. On the right-hand side, T of 0 plus theta of 1, theta of 2, all the way through theta of n. T of 0 is constant time. So this is what? Theta of 1 plus 2 plus 3 plus all the way through n. It is what? Arithmetic series. So theta of n squared. Another way to solve this recurrence equation is using recursion tree. Remember the recursion tree? Let's do recursion tree. So T of n equals T of 0 plus T of n minus 1 plus theta of n. So this T of n can be rewritten by a tree-like structure, like theta of n, and then T of 0 plus T of n minus 1. Theta of n as a root, and T of 0 and T of n minus 1 to its two children. Okay, T of 0 is simply theta of 1, so you have nothing to do. But what is T of n minus 1? Original formula is like this. So T of n minus 1 equals T of 0 plus T of now n minus 2. 1 less than n minus 1 is n minus 2 plus theta of n minus 1. So again, you rewrite T of n minus 1 using the formula. Theta of n minus 1, and then T of 0, and then T of n minus 2. And then we keep going on. I believe I have that in the next slide using recursion tree. T of n is Cn, T of 0, T of n minus 1. It was theta of n before, but theta of n is same as some constant C times n. So let's say just Cn. So Cn, and then T0 and Tn minus 1, T0 and Tn minus 1. again, you rewrite T of n minus 1 using original formula. T of n minus 1, T of 0 plus T of n minus 2 plus C times n minus 1. So we have something like this, and it keep going on. Now, T of n is addition of these three terms. T of n in this tree is addition of all the nodes of this tree. All the nodes. You have to add all these nodes in the tree. That is your T of n. So, on the right side, what would you think about the height of the tree? How far this tree goes from C of n to theta of 1? What's the height of this tree? N, n minus 1, n minus 2, n minus 3, all the way through 1. So, n, right? The tree is n. So adding this part is nothing but sigma k equal 1 through n, k. 1 plus 2 plus 3 plus all the way through k. To be specific, I might need to put c here, c times k, but it doesn't really matter because c is constant. And then T of 0, this is what? Constant time. We have constant time leaves. How many of them? Total. N of them. So n times constant time factor. This is what? Theta of n. So theta of n will be added to theta of n squared. You concentrate on the leading term. N squared is a leading term. So it is what? Theta of n squared. That's the worst case scenario. Okay. How about the best case scenario then? Every time you pick some magic partition value, so it can evenly distribute first half and second half with the same size. Every time you call partition, then the equivalence will look like this. T of n equals, after the partition theta of n, you have two exact size, T of n over 2. You have to sort both sides, so 2 times T of n over 2. This is same as the merge sort recurrence equation. You can use Maxwell method. This is theta of n log n. This is what? Best case scenario. What happens in between best and worst case scenario? Meaning, let's assume every time you do a partition, one half will be the size of 1/10, and the other half will be the size of 9/10. So every time you do a partition, the size of this guy is 1/10, and size of this guy will be 9/10. Is it closer to best case scenario or worst case scenario? What do you think? Every time you split your array into two subarrays in the size of 1/10 and 9/10 through partition, is it closer to best case, do you think, or the worst case? Best case is what? Exact half, right? 1/2 and 1/2. That's the best case, which is this. So let's choose some hypothetical split ratio 1/10 and 9/10, which look like what? Best or worst case?
Worst case.
Well, you can say worst case. Then guess what? If you keep split 1/10 and 9/10, the recurrence will be something like this. Why? Well, theta when coming from the partition, every time you partition, one size of your subarray will be 1/10. So the running time will be T of 1/10 n. The other side will be 9/10 of the original size. So T of 9/10 n. Yes? Now, can you solve this recurrence? Yes, using recursion tree again. So T of n. Now, one side 1/10 n, the other side 9/10 n. You keep replace term using the original formula, then we have something like this. Recursion tree method. Exactly what we did several times from the merge sort and so forth. Now, the interesting thing here is the length of the branch is not exactly the same. Some will be shorter than the other, or some will be longer than the other. Question is, which path is the shortest path? Which branch? Which branch you can hit to theta 1 in the shortest amount of time? This branch, or 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 this branch, among many branches. Which one? The leftmost branch. Why? Because leftmost branch, each level, you take 1/10 of the original size. When you go to second level, the size shrunk to 1/100th already. Compared to the rightmost branch, it only shrunk by 9/10 at each level. So rightmost branch is the longest branch. Leftmost branch will be the shortest branch. Agree? Then this T of n is addition of all the nodes in this recursion tree. So let's try to add everything here. The first level, Cn. Second level, you add 1/10 Cn plus 9/10 Cn, which is again Cn. The third level, if you add 100 Cn plus 900 Cn plus 900 Cn plus 8100 Cn, it'll be Cn as well. So it'll be Cn all the time until you hit the shortest leap. After this point on, because some leaves are already falling out, it is less than Cn, less than Cn. Keep going on up until the lastmost rightmost branch. Can I compute this? We need to know the length of the leftmost path and the rightmost path, which is what? The shortest and longest branch. The shortest branch, each time you become 1/10. So this is what? Log n with base 10. How about the rightmost? Each time you become 9/10. 9/10. So log n with 10/9 base. That is constant factor difference in terms of the base. So there is all log n height. Since each level is Cn and height is log n, it is what? N log n. Meaning, looks like it looks quite bad split, but still it gives you a theta of n log n, order of n log n time. Understood? Next thing we want to experiment is, then how about we alternate best case and the worst case in succession? Meaning, lucky case and unlucky case. Lucky case meaning each time partition split your subarray into exact half size. Unlucky case, meaning every time you split, one side you have nothing, another side you have n-1 element. So let's say lucky case with this L of n. Because it's lucky, you split exact half, n/2. But next level is unlucky case. This will be not L, but U. 2 times U of n/2 plus theta of n. Theta of n is, of course, from the partition. Each time you call unlucky case, after the partition theta of n, one side is nothing, the other side is everything other than the pivot, n-1 element. But after unlucky, you'll be lucky, so it'll be L of n-1. So this is what? Lucky and unlucky in alteration. Understood? So try to find recurrence equation when you have a lucky case and unlucky case, lucky case and unlucky case in succession. What will it look like in terms of recurrence equation? Well, we can solve this. U of n is equal to L of n-1 plus L of n. So you just put here inside L of n. So L of n equals 2 times L of n-2, n over 2 minus 1 plus theta of n plus theta of n. So you see what am I doing here? L of n equals 2 times unlucky. Well, now we are using this. Un is L of n-1 plus L of n. But what is U of n over 2? It is L of n over 2 minus 1 plus theta of n over 2. According to this. That is same as U of n over 2, this entire thing. Plus theta n. Now, if you solve this formula, it is what? 2 times L over n over 2 minus 1 plus 2 times L over n over 2 plus theta of n, which is theta of n combining both asymptotically. 2 times theta of n over 2, which is just theta of n. And this negative 1, you can just ignore when n gets bigger and bigger. So it is same as what? 2 times L of n over 2 plus theta of n, actually. Close enough. This is n log n, actually. So as you see, even lucky case and unlucky case alternate. The overall running time is like lucky case. So what do you know from this experiment? Unless you are really unlucky each time, every time you partition, one side nothing, another side everything other than pivot n-1 element. Every single partition time you do that, unlucky case, then yes. Then you hit the worst case scenario, which is theta of n squared. Each time you hit unlucky case, you have theta of n squared. Otherwise, it will be theta of n log n. Even you split 1/10 and 9/10, and when lucky and unlucky in alteration, they all fall into n log n time. So when it comes to quicksort, all you need to do is avoid this worst case scenario. So how can I avoid this worst case scenario? Relate to one of your questions before. should I always pick leftmost element when you do partition? If you pick always leftmost element, if input happen to be solid or reverse solid, we fall into worst case scenario. But if first time you pick leftmost element as your pivot, second time, let's say you hit third element as your pivot, some randomly, then you can avoid this worst case scenario. This is something called the randomized quicksort, which is actually outside of this semester's material. So I'm not going to go there to randomize quicksort. That is so-called the code tuning. You can easily tune the original quicksort code, and you can avoid the worst case scenario and close to n log n time. And how? So-called randomized quicksort, meaning when you get an input, you never know this input is already solid or reverse solid or totally out of order. You never know. So one method is rearrange your input randomly. So first element go to, let's say, in the middle. Second element go to, let's say, 10th element. Just spread your element randomly. Maybe it takes linear time to go through your entire input array. And then use this naive quicksort algorithm. Because you distribute your original input randomly takes just linear time, this randomized quicksort overall doesn't hurt because n log n time is bigger than the linear time anyway. Another way is when you choose your pivot, do not blindfoldly choose the leftmost element as your pivot. Each time you choose random element as your pivot. The first time, leftmost element. Second time might be rightmost element. Third time, middle element, let's say. If you choose your pivot randomly, you can avoid this worst case scenario. As long as you avoid this worst case scenario, your running time of quicksort is 0 of n log n, order of n log n time. So it is just great general purpose sorting algorithm because code tuning is quite easy and it's in place sort, doesn't need any extra storage space, unlike a merge sort, and achieve n log n time. Same time as a merge sort, even better because, again, as I said at the beginning, we don't need time to reserve extra memory space. This is why quicksort appeals so much to many people in the industry. So let's say in C++, you're calling library function sort. The chances are you're actually using quicksort underneath. So-called randomized quicksort. Again, running time, n log n, same as merge sort asymptotically. But you do not need any extra memory space. It's in place sort. You just rearrange your original input in your own array. Any question? So this is chapter, I believe, 7. So please, I'm gonna put some homework questions from this chapter as part of your next homework. And without really getting your hands dirty, you do not really learn anything. So try to exercise, try to solve the homework problem. And why don't you actually run the code of the quicksort, even though I didn't give you this as a separate project. And compare the overall running time with the merge sort or insertion sort. Any question? Okay, so I'm gonna stop here. And this Thursday, we're gonna move on to the next chapter, chapter 8. Okay, so again, step number 1, to fully understand the quicksort, what you need to understand? The partition. It is all about the partition. The rest of the quicksort is just trivial. So as I said, sometimes it is simply called just recursive partition. That is all about the quicksort. Like recursive merging, there is a merge sort. So you have to understand the most important part of today's lecture is you have to understand this partition routine. That's a key. Any question? Okay, so I'll see you on Thursday. And don't forget to submit your homework by tonight if you have not done so far.